Again, let's greetings. Let's talk about more from section 2.5. Here's number 54. In the theory of relativity, the mass of a particle with velocity v is given by m equals m sub 0 or m naught divided by the square root of 1 minus the quantity v squared over c squared. And then they say where m naught is the rest mass of the mass of the particle at rest, and c is the speed of light. What happens as v approaches c from the left? So I just want you to take the limit as v approaches c from the left. So taking the limit of m, um, but m is m naught over this square root expression here. What's the first thing I tell you to do or try every time you're taking a limit? First thing I tell you to try is, hopefully you're saying it before I do, direct substitution. The numerator is a constant as far as v changing. And then the denominator, I'm going to replace that v with c, and I'll get c squared over c squared, which is 1 minus 1 is 0, square root of 0 is still 0. So this is going to m naught over 0. Again, m naught is not 0. It's a non-zero constant, the rest mass of the particle. So I've talked about this before, and you got to start thinking this way. Whenever you end up with a non-zero constant in the numerator and 0 in the denominator, then the limit is going to be approaching one of the infinities. The graph will have a vertical asymptote at the value that x, or in this case v, is approaching. And so at that point, we just try to figure out, are we approaching positive infinity or negative infinity? Since m is mass, that's going to be a non-negative number. So in this case, it's going to be positive. And if you remember the definition of the square root full name is the non-negative square root. And so the denominator is non-negative and getting closer to 0. And so it's going to be a positive over a positive number. And so that'll be going off to positive infinity. What this is telling you, believe it or not, but this is the physics of it, is that as an object travels faster and faster, it gets heavier and heavier. Okay, its mass is growing without bound. We don't see that in everyday life because we're not traveling very fast. The speed of light is a very large number. I want to say it's like 3 times 10 to the 6 meters per second or something like that. I might be off in my units. If I am, please don't chastise me. I didn't look it up ahead of time, and it's not something that I've committed well to memory. But nonetheless, it's really, really fast, and you don't see this in everyday life because, in other words, what's happening is the velocity that you're moving at when you're, say, in your car or something is really, really small compared to the velocity of light. And so this quantity here is really, really close to 0. And some 1 minus something really close to 0 is really close to 1. The square root of something really close to 1 is still really close to 1. And so m naught divided by something close to 1 is still really close to m naught. So you're never going to notice a difference. We don't even have, for driving in a car, we don't have precision enough in our instrumentation of measurement to be able to tell uh, a difference in the mass. So now, why is a left-handed limit necessary? A left-handed limit is necessary because if v approaches c from the left, I know this question wasn't asked, but it was asked at another time, and you should understand it. If v is approaching c from the left, it means v is smaller than c, so that means v squared is smaller than c squared, so this is less than 1. Everything works out nicely. But if v was approaching c from the right, v would be bigger than c, so v squared would be bigger than c squared, and this fraction would be greater than 1. 1 minus something greater than 1 would be negative, and then we'd end up with a non-real root. So that's why we want v to approach c from the left. Now number 55. It says a tank, part A says a tank contains 5,000 liters of pure water. Brine that contains 30 grams of salt per liter of water is pumped into the tank at a rate of 25 liters per minute. Show that the concentration of salt after t minutes in grams per liter is given by that function there. And then in part B, you're asked what happens to the concentration as t approaches infinity. You don't need my help for part B, and I'm not going to give it to you beyond what I'm about to mention. They gave you the function for C. I know part A asks you to derive it, but you have the function. So to answer part B, just take that limit as t goes to infinity, and our techniques that we were taught in class will be able to handle that. So you don't need help with B. I will help you with A, and again, you don't need help with B. So that's our function. I put grams per liter off to the side. What we should pay attention to here are the units, because the units are going to help you figure out what's going on. A lot of students tend to ignore the units and just try to slap them on at the end of their answer, hopefully hoping to get it right. But if you really think carefully about the units and how they are manipulated through the process, you can often learn a lot about how things are related, or you can put things together in the proper relationship to get the correct answer. So we're going to utilize the units quite a bit. It says the concentration is in grams per liter, so I note that off to the side of the function over here. The numerator has to be some number of grams, and the denominator has to be some liters. In the numerator, grams of salt, and in the denominator, liters of water. So as I start to create this function, I got to figure out how to get some number of grams of salt in the numerator. So let's go back to the text. So brine that contains 30 grams of salt per liter of water is being pumped in the tank, okay, at a rate of 25 liters per minute. We'll come back to that part in a minute. 30 grams of salt per liter of water. So if I have 1 liter of water, I have 30 grams of salt. If I have 2 liters of water, I have 60 grams of salt. If I have 25 liters of water, I have 30 times 25 grams of salt. And notice the water's coming in at 25 liters every minute, okay? So I'm going to go, I got 30 grams of salt per liter of water times 25 liters per minute. So that's how many grams are coming in every minute. Let's watch how this plays out here a little bit. I know it might be hard to see. Let me write this over here. So my units are grams per liter times liters per minute. So if I actually just think of these as variables or quantities, I could cancel the liters here, and I'm left with grams per minute at this point, okay? I don't want grams per minute, so the liters are going to cancel. I want grams, not grams per minute. So I have to multiply this by some time in order to figure out just the number of grams after t minutes. Well, there's the answer right there. I need to multiply this by t minutes. Because if I multiply this by t minutes, now the minutes are going to cancel over here, and I'm going to have 30 times 25 times t grams. Grams are the only units left up here, which is what I want. I want grams on top. So I have the numerator with the correct units. Hopefully this works out the way it's supposed to. Let's go to the denominator. Now, so the denominator's liters, so it's some amount of water. We know it starts with 5,000 liters of water, and then we're adding in 25 liters every minute. Okay, it's the brine, but the brine has two things in it, salt and water. So the salt we've already taken care of. Now we're talking about the liters of water. So it's 25 liters coming in every minute. So if I'm going to add to this 25, well, this is liters per minute. I can't add liters with liters per minute. So I got to actually get this into liters. And I got these pesky minutes here that I want to get rid of. So we'll do what we did in the numerator, and we'll multiply by t minutes. And the minutes will cancel here. I'll have 5,000 liters plus 25 t liters over here. So when you get rid of all the extra stuff here, this becomes 30 times 25 times t grams. I'm going to move the units to the outside, over 5,000 plus 25 t liters. This is actually this, if you do the little bit of algebra that it takes to figure that out. So go do that little bit of algebra, and then go on and do part B.